Hello everyone. Welcome to JCE Connect online classes. Let's continue with the module 4 Embedded System Design Concepts Fundamental Topic Program Modeling. In the previous video lecture, we have seen three computational programming models: data flow graph, control data flow graph, and state machine model. In that finite state machine model examples also we have discussed. So in this video lecture, let us look into another three computational programming models: sequential program model, concurrent program model, and object-oriented program model. Now let's look into another programming model, that is sequential program model. In case of sequential program model, all the functions or processing requirements are executed in a sequential manner, and it is considered as same as that of conventional procedural programming language. In this, the program instructions are iterated and executed conditionally, and also the data get transformed through a series of set of operations. Usually, finite state machines are the best choice for sequential programming models. Also, we have another important tool that is mostly preferred in sequential programming model, that is flowchart model. The finite state machine approach represents the states, events, transitions, and actions, whereas flowchart model models the execution flow of the code. So let us consider the same example what we have taken before to explain the remaining programming models, that is seat belt warning system. The flowchart of the same is given here. Let us understand the flow of the execution of the code. So initially what happens with the flowchart here is it waits for 10 seconds to ignition key on. Okay, after waiting for 10 seconds, it will check whether the ignition is on or no. If ignition is on, that means if yes, then it checks whether the seat belt is on or no. If the ignition is on as well as seat belt is on, then it ends the program execution. If the ignition is on and the seat belt is not on, then it will set the timer for 5 seconds and start the alarm. After starting alarm, again it will check whether the ignition is on. If the ignition is not on, then it will end the program. If the ignition is on, then it will check for whether the seatbelt is on or no. If the ignition is on and seatbelt is not on, then it checks whether the timer has expired or no. That is what 5-second timer that you have set before. If the timer has expired, then it will stop the alarm and end the execution. If the ignition key is on and seatbelt is not on and the timer has not expired, then go on checking the same ignition on seatbelt on condition till alarm expire event occurs or seatbelt on condition occurs. If the timer expires or the seatbelt on condition occurs, then stop the alarm and end the program execution. So this is how sequential program model for seatbelt warning system with the flowchart model is performed. Let us understand another programming model, that is concurrent or communicating process model. The concurrent or communicating process model models concurrently executing tasks or processes. So far we have discussed about sequential execution of software programs. It is easier to implement certain requirements in concurrent processing model rather than using sequential execution model. Sequential execution model leads to a single execution of a task and thereby leads to poor processor utilization or CPU utilization when the task involves input-output waiting, sleeping for a specified duration, etc. If we divide the task into multiple subtasks, it is possible to tackle the CPU usage effectively when the subtask under execution goes to wait or sleep mode by switching it to the task execution back. However, concurrent processing model requires additional overheads in task scheduling, task synchronization, and communication. As an example for the concurrent processing model, let us examine how we can implement the seat belt warning system in concurrent processing model. So we can split the tasks into following. So let us consider the first one. Timer task for waiting 10 seconds, that is called as wait timer task. Second one is task for checking the ignition key status monitoring task. Third one is task for checking the seat belt status, that is seat belt status monitoring task. And the fourth one is task for starting and stopping the alarm, that is alarm control task. Fifth one is alarm timer task for waiting 5 seconds, that is alarm timer task. The table shown here depicts the task for seat belt warning system. First one is create and initialize events like wait for timer expire, ignition on, ignition off, seatbelt on, seatbelt off, alarm timer start, alarm timer expire. And second one is create task wait timer. Third one is create task ignition key status monitor. Fourth one is create task seatbelt status monitor. Fifth one is create task alarm control, and the last one is create task alarm timer. So in this we have 5 tasks and we cannot execute them randomly or sequentially. We need to synchronize their execution through some mechanism. So we need to start the alarm only after the expiration of 10-second wait timer, and that too only if the seat belt is off and the ignition key is on. Hence, the alarm control task is executed only when the wait timer is expired and if the ignition key is in the on state and seat belt is in the off state. Here, we will use events to indicate these scenarios. The wait timer expire event is associated with the timer task event, and it will be in the reset state initially and it is set when the timer expires. Similarly, events ignition on and ignition off are associated with the task ignition key status monitoring, and the events seatbelt on, seatbelt off are associated with the task seatbelt status monitoring. The events ignition off and ignition on are set and reset respectively when the ignition key status is off, and reset and set respectively when the ignition key status is on by the ignition key status monitoring task. Similarly, the events seatbelt off and seatbelt on are set and reset respectively when the seatbelt status is off, and reset and set respectively when the seatbelt status is on by the seatbelt status monitoring task. The events alarm timer start and alarm timer expire are associated with the alarm timer task. The alarm timer start event will be in the reset state initially, and it is set by the alarm control task when the alarm is started. The alarm timer expire event will be in the reset state initially, and it is set when the alarm timer expires. The alarm control task waits for signaling of an event wait timer expire and starts the alarm timer and the alarm if both the events ignition on and seatbelt off are in the set state when the event wait timer expire signals. If not, the alarm control task simply completes its execution and returns. In case the alarm is started, the alarm control task wait for signaling of any one of the events, alarm timer expire or ignition off or seatbelt on. Upon signaling any one of these events, the alarm is stopped and the alarm control task simply completes its execution and returns. Here it should be noted that the method explained here is just one way of implementing the concurrent method or concurrent model for seatbelt warning system. The intention is to just make the reader familiar with the concept of multitasking and task communication or synchronization. The concurrent processing model is commonly used for the modeling of real-time systems. Various techniques like shared memory, message passing, events, etc. are used for communication and synchronization between concurrently executing processes in this. And the last programming model which we are going to discuss is object-oriented model. The object-oriented model is an object-based model for modeling system requirements. It disseminates a complex software requirement into simple, well-defined pieces called objects. Object-oriented model brings reusability, maintainability, and productivity in the system design. In this modeling, object is an entity used for representing or modeling a particular piece of the system. Each object is characterized by a set of unique behavior or a state. A class is an abstract description of a set of objects, and it can be considered as a blueprint of an object. A class represents the state of an object through member variable and object behavior through member functions. The member variables and member functions of a class can be private, public, or protected. Private member variables and functions are accessible only within the class, whereas public variables and functions are accessible within the class as well as outside the class. The protected variables and functions are protected from the external access. However, classes derived from a parent class can also access the protected member functions and variables. The concept of object and class brings abstraction, hiding, and protection. Thank you everyone for watching.